So here let us write the second theorem that we're going to cover. This is global asymptotic stability theorem. In the earlier theorem, we have seen the local stability conditions. So we could only claim local stability or local asymptotic stability based on the theorem given earlier. So the functions, for example, in that case were only locally positive definite or locally negative definite or negative semi-definite. In this case, this theorem is going to require actually stronger conditions to hold for claiming global asymptotic stability of the equilibrium point. Let's write the theorem first. Consider the system x dot is equal to f of x. In this case, f of 0 is equal to 0, so equilibrium point is at the origin. If there exists a continuous scalar valued function v of x with continuous partial derivatives. Such that v of x is globally positive definite. So theorem is going to claim global asymptotic stability, so we're going to need global positive definites. And v dot of x is globally negative definite. And we have a third condition. These two conditions, unfortunately, are not sufficient. So v of x goes to infinity as norm of x goes to infinity. Okay? The name of this third condition is radial unboundedness. Then, the equilibrium point xe is equal to 0 is globally asymptotically stable. In the sense of so in general, if I have a locally positive definite function, then the function touches 0 at the origin, and it is positive everywhere in a small ball. Okay. In that case, if you look at the level curves of that function, the level curves are always going to be looking like this locally. Okay. So if a function is locally positive definite, then we know that its level curves are actually looking like closed curves like this around origin, because the function hits 0 only at a single point, and it is positive everywhere else. So the function is ball-like near the origin. Okay, but here we need and level curves being in closed contours like this is actually useful for us to claim asymptotic stability. We know that if the level curves are looking like this everywhere, and if v is getting smaller and smaller, in that case we would always know that there is convergence towards the equilibrium point. If the level curves are actually looking like this in the whole space, and if v is globally positive definite, if the level curves are like this, and if v dot is globally negative definite, then we will be sure that in that case, because the V is always getting or going to get smaller and smaller, for any initial condition, we would be able to guarantee that convergence happens to the equilibrium point. Okay, but we need to ensure that all level curves are actually these type of closed contours. Unfortunately, so all locally positive definite functions have their level curves close to the origin looking like this, but unfortunately globally positive definite functions, although they have level curves very similar to this near the origin, sometimes they might have level curves which are not closed curves anymore. Okay? So that is what this third condition is guaranteeing. It is actually guaranteeing that the global positive definite function that we are working with has level curves like closed curves everywhere in the whole state space. Okay? So sometimes if this condition is not guaranteed, then the level curves of a globally positive definite function might be actually some curves which are not closed, similar to these. Okay, so and those would make the theorem actually inconclusive in that case. Okay, that is why the third condition is actually assumed here. If the third condition, if the radial unboundedness is assumed, then we will be able to guarantee that the level curves of V are actually closed contours everywhere in the state space. The first thing that we will do here is that we will try to understand what this radial unboundedness means. Okay? What this condition would actually mean, and I will give you a function which is globally positive definite but not radially unbounded. Okay? So then we will try to talk about what can happen in that case, which would make this theorem inconclusive in that case. Okay? So here, radial unboundedness means this thing. If I have my state space, this is my x1, x2 space, I need to look at these type of radial lines. These radial lines are actually going towards infinity, and they are departing from the origin, and they go to infinity like this. And these are the radial lines that we consider. On each of these lines, norm of x would go to infinity. Okay? On each of these lines, if I move in that direction, the norm of x would go to infinity. So what the radial unboundedness condition assumes is that if I go on this line, when norm of x goes to infinity, v of x should go to infinity on that line as well. Okay? That is what radial unboundedness condition means. On all of these lines, the function v of x should actually diverge to infinity. Okay? So I can actually show you an example where this actually happens. x1 squared plus x2 squared. Okay? That is v of x. Okay? Is this function radially unbounded? So do you think going on all of these lines, on each and every direction, okay? Going on all of these lines, does this function diverge to infinity? So do you think we have radial unboundedness condition in that case? Yes, actually this is nothing but norm x squared. Okay? It really doesn't matter whether I have this function or the following function, 2x1 plus 3x2 squared. Okay? I can consider this function. This is also radially unbounded. Okay? So going on all of these lines, if either I know that if I'm on these lines, either x1 or x2 are going to either one of them are going to diverge to infinity. Okay? And I know that both of these functions would diverge to infinity if norm of x would diverge to infinity. Okay? So both of these functions are actually radially unbounded functions. And their level curves, the level curve of this function, they are circles. Okay? and these circles will continue until infinity. And the level curves of this function, they would be ellipsoids. Okay, so the ellipsoids would be maybe looking like this. They have all closed curves in the whole space as their level curves. So if on a trajectory of the system, if these functions get smaller and smaller at each time instant, I would know that the motion of the system trajectories would be towards inside. Okay. Now I will give you an example where this function is not radially unbounded anymore. Let us look at an example. And in this case, the function is going to be the following. X is equal to x1 squared divided by 1 plus x1 squared plus x2 squared. Let us consider this function. By the way, both of these functions are globally positive definite. Globally positive definite. Okay? Let us try to look at this function. Is this function radially unbounded? And the answer is actually going to be no. Okay? But let us first look at sign definiteness. So do you think this function is positive definite? So here, I know that this term is always larger than or equal to 0, and this term is also larger than or equal to 0. Okay? So for this function to be equal to 0, v of x is equal to 0, then both of these terms should be equal to 0. So in that case, x1 squared divided by 1 plus x1 squared is equal to 0, and x2 squared is equal to 0. But these would mean that x1 is equal to 0 and x2 is equal to 0. Okay? So we see that this function is 0 only at the origin. Okay? The function is 0 only at the origin, and it is non-zero everywhere else. Okay? So that actually makes this function globally positive definite. V is globally positive definite. Okay? But let us see if it is actually radially unbounded or not. Right? So here, what I'm going to do is that I will look at norm of x. I will make x diverge on any of these lines. Okay? And I will try to check if v is going to diverge on these lines as well or not. Okay? So here I see that if on these lines, if x2 magnitude goes to infinity, if magnitude of x2 goes to infinity on one of these lines, then v of x is going to go to infinity. Okay? On all of these lines where the magnitude of x2 would go to infinity, in that case, that v of x is going to go to infinity. Okay? That actually means that I need to concentrate on lines where x2 is not going to infinity. In this figure, on which radial lines does x2 not go to infinity? Or the horizontal lines, okay? So I need to concentrate on these horizontal lines. So either this one or this one. So I need to check what happens on these lines. If on these lines v of x goes to infinity, then the function would be radially unbounded. Okay? Because on any other line, v of x would go to infinity. Okay? And I need to check whether on these green lines the function would go to infinity or not. How can I parameterize such a green line here? How can I parameterize? So that line can be parameterized as a non-zero real part and non-zero x1 part and 0 x2 part. Okay? And then I can think about what happens when alpha goes to infinity. Okay? So let us consider the following. Limit, let us say that when x is alpha 0 and the right green line is going to be the case when alpha going to infinity. What is this limit? Limit of v of x as x is equal to alpha 0 and here alpha goes to infinity. Okay? Here I can look at the following limit. This is limit as alpha goes to infinity v of alpha 0. Okay, I can look at this. So in this case, do you think norm of x would go to infinity? Do you think in this case, yes, the norm of x is going to go to infinity. So I'm checking if this property is actually satisfied. When this is satisfied, is this satisfied? Okay. So here, what is this limit? This is going to be, so I will substitute alpha 0 in v of x. Okay? That is going to be alpha squared, 1 plus alpha squared, plus 0 squared. Okay? And I will be taking the limit of this thing as alpha goes to infinity. What is this limit? 1. So what can you say about this function? Is it radially unbounded? No. Because as the norm of x goes to infinity, v of x really does not go to infinity on this green line. Okay? That is why this function is not a radially unbounded function, unfortunately, and it doesn't satisfy the requirements of the theorem. So here I will try to draw the level curves of such a function. Okay? I can actually draw the level curves of this function as follows. So this is my x1, x2 here. The level curves of such a function, if x1 is very small, the level curves would be like circles. If this thing is very small compared to 1, in that case the level curves will be very similar to the level curves of those circles. Okay? So the level curves for small x, they are closed curves looking like this. But if x1 is very, very, very large, in that case, this thing is going to be approximately 1, and the level curves would start to be something like this. Okay? I'm not drawing it because I know this function. I'm drawing this from memory. Okay? It's not something I can draw in general. Using a computer would be much better in this case. So the level curves of increasing v can be actually drawn for this function looking like this. So let us try to say this is, for example, v is equal to 0.1, 0.2, 0.3. So here after some magnitude here, the level curves would start to become like this. They are still inside each other, but the level curves are actually looking like this. They are no longer closed curves. Okay?
Hocam, if that value is 1,
I'm not sure. I'm not sure about when this change happens at some level curve value, but I'm not sure about the exact value of the change between this type of curve and this type of curve.
But can we say it's close to 1?
Yes, we can actually say that, because only when x1 is small, when x1 is close to 1, this change is going to happen. If x1 is much smaller than 1, the level curves would be closed curves in that case. But if x1 is close to 1, in that case level curves would change their property. Okay? Yes, you can actually say so. So now I will actually give you a trajectory. What does this theorem tell us? The theorem tells us that v of x is globally positive definite, and this function is actually telling us the same. Yes? Mm-hmm. 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 V of x 1'e doğru converge ediyor. Arkadaşınız şunu sordu diye anladım ben. Yani level curve'ler bir yere kadar closed curve'ler, tamam mı? Ama bir yerden sonra level curve'ler şey yapmaya başlıyor. Level curve'ler böyle closed olmayan curve'lere dönüyor. O transition'ı sordu diye anladım arkadaşınız. Yani şurada 0,1, 0,2, 0,3 bunlar böyle v of x eşittir 1'e kadar devam ediyor. V of x birden büyükse de böyle açılmış curve'ler oluyor diye anladım. Okay. So in this case, what does this function satisfy? This function satisfies the globally positive definite property, but it does not satisfy this radially unboundedness property here. Okay? So here, suppose that this condition was not here. Okay? Suppose that this condition was not here in the theorem. And suppose that I have a system with the following trajectory. Suppose that I have a system with the trajectory given like this. Okay? So suppose that I have a trajectory of the system going towards this line. Okay? Suppose that I don't have this third condition here. Okay? So v of x would satisfy all of the properties of this theorem. V of x is globally positive definite. It satisfies this property. So suppose that I have a system whose trajectory is doing such a motion. Okay? What can you say about v dot in this case on the trajectory of this system? So v is increasing on these curves. Okay? What can you say about the v dot on this trajectory of the system? V is getting smaller and smaller as this trajectory is crossing these level curves. Okay? V is getting smaller and smaller as this trajectory crosses these level curves. Okay? So V dot is actually negative on that trajectory. Okay? So in such a case, what would have happened? V of x is globally positive definite. V dot is actually negative all the time. In that on that trajectory I have negative V dot. And in that case, if this third condition is not here, the theorem would tell us that that trajectory should converge to the equilibrium point at the origin. Okay? But is it converging to the origin? Without this condition, this type of function and this type of system would give us a wrong conclusion. Yes?
As we go to infinity, wouldn't V dot go to zero?
V dot would go to zero as we go to infinity. Going to zero would not mean that it is going to be zero. Okay? Going to zero, this function would go to zero, e to the minus t. It is going to zero, but it is always positive. Okay? So the function would still be negative definite. Okay? So here, as you see here, without this condition, when this condition is not satisfied, in that case the system might not be globally asymptotically stable, but because the system would have a trajectory that is diverging away from the equilibrium point. Okay? So that actually means that for this theorem to be actually correct, we are required to keep this radially unboundedness condition. So we cannot consider functions which are not radially unbounded in global asymptotic stability theorem. For local asymptotic stability, we don't have any problems because this function would already have closed level curves in a small region around the origin. So finding just a small ball in which the level curves are actually closed curves is going to be sufficient for local asymptotic stability. But for global asymptotic stability, we are required to have level curves as closed curves everywhere in the state space. Okay? That is why this theorem, because it is related to global asymptotic stability, we are required to keep the radially unboundedness condition. So here this was the explanation of why we need radial unboundedness condition. And now we are actually ready to solve an example.
Hocam,
Yes.
baktığında trajectory you just
No. So here, this is the trajectory of an example system. Okay? If I have a trajectory of an example system that is going from here to here, then v dot of x is going to be negative on that trajectory. Why is that? Because these level curves are going in increasing v of x direction. This is v of x is equal to 0.1 curve. It is equal to 0.2 curve, 0.3, and let us say that this is v of x is equal to 1.5, 1.6, 1.7, etc. So on this trajectory, v of x is going to get smaller and smaller, meaning that v dot is negative on this trajectory. Okay? So what do we want for global asymptotic stability? For global asymptotic stability, we want v dot to be negative everywhere. Okay. So and if v is global, we want v of x to be globally positive definite, and v dot to be negative, and in that case, if those conditions are satisfied, we would like to be able to say that this green trajectory is going to converge to the origin. But it's never converging to the origin. It's diverging to infinity. Şimdi burada şöyle bir durum var. Yeşil trajektörü bir örnek bir sistemin trajektörisi. Şimdi bu V'yi bu teoremde kullanabiliyor olsaydım, yani şu üçüncü koşul geçerli olmasaydı, aslında durum şu olacaktı. V globally positive definite, V dot negatif olduğu zaman, o zaman bu trajektörü orijine konverge etmesini isteyecektim aslında. Çünkü globally asymptotically stable demek aslında bütün trajektörlerin her yerden başlatılan trajektörünün orijine converge etmesini istiyorum manasına geliyor. Ama bu örnekte görüldüğü gibi eğer fonksiyon radially unboundedness özelliğini sağlamazsa o zaman v dot'ın negatif olması orijine converge etmek manasına gelmiyor. Bunun böyle olmasının sebebi şu konturların close kontur olmaması. Eğer konturlar her yerde şunun gibi olsaydı o zaman v dot negatifken ben her zaman orijine doğru converge ediyor diyebilecektim bütün trajektörler için. Ama bu durumda v dot negatif olmasına rağmen, yani v her durumda azalıyor olmasına rağmen orijine bir convergence gerçekleşmiyor. Dolayısıyla teorimi bu koşul olmadan kurduğum takdirde V globally positive definite zaten öyleydi. V dot gerçekten globally negative definite. V dot'ın negatif olduğundan eminim. Ama teorem bana şey diyecek, bu sistem globally asymptotically stable diyecekti. Ama benim böyle bir trajektörüm olacaktı şeyden uzaklaşan. Equilibrium point'ten uzaklaşan. Dolayısıyla teorem tamamıyla yanlış olacak. O yüzden yaptığımız şey üçüncü koşulu getirerek bu fonksiyonu, yani demin verdiğim radially unboundedness koşulunu sağlamayan fonksiyonu tamamıyla devreden çıkarmak oluyor.
Orijinde sıfır olduğunu da göstermek gerekmiyor mu?
Orijinde sıfır olduğu bariz değil mi? Yani orijinde equilibrium noktası var sistemin. Dolayısıyla sistemi ben burada bırakırsam esasında x dot'lar sıfır olacağı için v dot'ın sıfır olması gerekir. Yani neden? Yani çünkü v dot dediğim şey del v over del x1 çarpı x1 dot artı del v over del x2 x2 dot. Bu durumda ben bu fonksiyonu orijinde evaluate edersem şu şey olmayacak. x1 dot eşittir f1 of x1 x2, x2 dot eşittir f2 of x1 x2. Dolayısıyla del v over del x1 f1 of x1 x2 yapacağım. Artı del v over del x2 burada f2 of x1 x2 yapacağım. Ben bunları orijinde evaluate edersem zaten bunların sıfır çıkacağını biliyorum equilibrium noktası olduğu için. Dolayısıyla v dot her halükarda orijinde sıfır olmak zorunda. Başka yerdeki bütün trajektörlerde bu aynı motion'u yapıyorlarsa v dot'ın her yerde orijin dışında her yerde negatif olduğunu söyleyebileceğim aslında. Dolayısıyla teoremin koşullarını şu olmasaydı eğer sağlayan bir sistem bulmuş oluyorum. Ama o sistem kesinlikle global asymptotic stable değil. Demek ki o fonksiyonu bir şekilde bu işin dışında tutmamız lazım. Onu dışında tutmamıza yarayan üçüncü koşul da bu koşul. Yani bütün konturları, bütün level curve'leri şöyle close kontur olarak birbirleriyle iç içe close konturlar olarak aldığımız takdirde o zaman V-dot'un negatif olması convergence manasına geliyor. Ama fonksiyonun level curve'leri bazı yerlerde böyle close kontur olmayıp şu hale dönüştüğü zaman o zaman V-dot'un negatif olması maalesef convergence manasına gelmediği için üçüncü koşulu yapıyoruz ki bütün level curve'ler bu koşulu sağlasın. Any other questions? So let us solve an example. X1 dot is equal to minus x1 plus x2. X2 dot is equal to minus x1 minus x2 minus x2 cubed. So here we are going to look at the stability of the equilibrium point at the origin with v of x given as x1 squared plus x2 squared. A very basic function. Actually, here I will just slightly change this, okay? So I will just put the following. X1 squared is given like this, but I will put the alpha, okay? And let us see what is going to happen. So the Lyapunov function now is dependent on an alpha parameter, okay? For global positive definiteness, what do I need for the parameter alpha? In our theorem, v of x is required to be globally positive definite. Okay? What is necessary on alpha for global positive definiteness? Can alpha be negative? If alpha is negative, the function is indefinite. Okay? In that case, can alpha be 0 for global positive definiteness? If alpha is 0, I get a positive semi-definite function. Okay? So alpha should be positive for global positive definiteness. Okay? If alpha is positive, then v of x is globally positive definite. Okay? And now I will be looking at what happens to v dot. Well, but before that, let us try to check radially unbounded condition. Okay? If alpha is positive, do you think we have radial unboundedness? On those lines, on those radial lines, if you diverge to infinity, if you let x diverge to infinity on those lines, do you think this is going to diverge to infinity as well? Yes. So v of x is radially unbounded. Okay? That is what I have. And now I'm going to calculate what v dot is. Obviously, v dot is going to depend on alpha, but you have to be careful to select alpha. Okay? So let us calculate v dot. V dot of x is equal to derivative of this thing with respect to x1. Then it is going to be the following. So I have 2 alpha x1. It is the derivative given like this. And I will have just this one, x1 dot, minus x1 plus x2. And I have here derivative of the function with respect to x2, 2x2 times x1, x2 dot, minus x1, minus x2, minus x2. Okay. So I get this. So I have v dot of x is equal to, I can write minus 2 alpha x1 squared, okay? And I have plus 2 alpha x1 x2, and I have minus 2 x2 x1, okay? Minus 2 x2 squared and yerde bir şeyler yanlış yapıyor muyum? Ona bir bakmam lazım. Yes. And minus I have 2 x2 to the 4. Suppose that you are given this function, okay, which is dependent on alpha, and you would like to make stability analysis. If you don't know the Lyapunov function, that is what you might actually try to do. If you don't know this Lyapunov function, you might start with a parameterized function, and you can try to find its parameters to conclude about the stability. When I calculate v dot, I want this thing to be negative definite or locally negative definite or locally negative semi-definite or globally negative definite or negative semi-definite. Okay? Here, by choosing an alpha value, specific alpha value, can you make this function v useful in concluding about the stability of the equilibrium point? Okay, that is the question. That is what you can actually do in practice. You might not know the Lyapunov function from the start, but you might be given some function which is parameterized. And then you can try to choose specific parameters for that function so that you can make some conclusion about the stability of the equilibrium point. Okay? So here, which terms are the terms that would make us unable to conclude anything? These cross terms. These cross terms are actually indefinite terms. Okay? Really, we do not like these terms so if these terms would remain here, the theorem would be inconclusive. Okay? So that is what I have to do while trying to choose alpha here. While trying to choose alpha, I need to try to cancel those indefinite terms. I know that these terms can be useful in my conclusion, and this term can be useful, this term can be useful. But here, if these terms would remain here, I would be unable to make any conclusion about the stability of the system. So that is why what should I choose alpha here? You see actually, to cancel this, choose alpha is equal to 1, which would make these indefinite terms cancel here. Okay? And that is going to give me, if alpha is equal to 1, I have minus 2 x1 squared and minus 2 x2 squared parentheses 1 plus x2 squared. Okay? I get this. Now what can you say about the sign definiteness properties of this function? It is 0 at the origin, that is good. And when is this thing exactly equal to 0? When is this thing exactly equal to 0? Is it 0 anywhere other than the origin? No, it is only 0 anywhere other than the origin. It is only negative everywhere other than the origin. That means that this is globally negative definite. Okay? And that would complete the satisfaction of all of the requirements of the theorem. Okay? And that actually means that this equilibrium point xc is equal to 0, 0 is globally asymptotically stable. We have a complicated differential equation for the system. Without solving it, we can conclude that the equilibrium point is globally asymptotically stable. What does this mean? Starting the system anywhere in the state space, the trajectory will converge to the origin. So this system trivially has an equilibrium point at the origin. Are there other equilibrium points? How can you say so? Are there other equilibrium points for this system? Why not? Because if there was other equilibrium points, that the equilibrium point at the origin cannot be globally asymptotically stable. Okay? Because if I start the system at the other equilibrium point, the system would have stayed there. There wouldn't be any convergence to the origin. Okay? That is why by the result of this theorem, I'm also sure that there exists no unequilibrium point of the system anywhere else. Okay? That is what we think. That's all for you. Thank you very much.